Hello students, welcome back. Now let's go to confidence bound problem. That is latter half of this problem set. Let's see. We have the data and the mean and standard deviation are. This is a mean. That is the standard deviation. And then over square root of 13. This is the standard error. So what do we have here? We have n is 13, and then the mean x is approximately equal to, we need approximation symbol, and that's this. And then standard deviation is approximately equal to this. And SE is S over square root of n, and that's approximately equal to this. All right. If you don't have Mathematica, then use MS Excel here. Mean, that's not too bad. You can use your calculator for that. But standard deviation computation is gonna be pain in the rear end. So use your MS Excel, or maybe you can do some web-based calculation tool for standard deviation. No matter what you do, I don't care. Use technology. And the standard deviation over square root of n, you can get the samples. You can get the standard error like this. Okay, confidence intervals, all right. Upper confidence bound, lower confidence bound. Okay, all right. Let's see. We want a sample size of 13, so okay, let's do this. And let's copy and paste this thing down here, and then let's work out either a lower confidence bound or an upper confidence bound. What do you like? I'd like to do the lower confidence bound because there's one more step to do. Okay, all right, we have the picture like this, and then the center, and then the end. So the t-score is end minus center over SE, and that's approximately equal to, let me increase the font, the left-hand side endpoint, and then the center, and what is it? Yeah, this sample mean, and then over standard error, this quantity. So this is standard deviation, that over square root of 13. So that's my standard error. We did this computation previously, so I'll just use that. And that is going to be approximately the same as the t-score. And please note that this is going to the left. So in standard t-curve, which is centered at 0, going to the left, so it should be negative something. Negative some t-star value. Okay? So t-score formula, end minus center over SE. So lower bound minus center over SE. That's going to be negative something. All right. Let's go to the t-table here. 95% confidence interval. All right, here's a t-table. Okay, here's a t-table. And the degree of freedom is 12, you see. Sample size is 13, so degree of freedom is 12. And then this probability here should be 5%. We have 95% here, 5% there. So where's 5%? 5% here, and down, 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 and 12. 1.782, do you see it? 1.782. So the degree of freedom of 12 and O5 column, 1.782. Okay, 1.782. That is my t-value associated to this problem. Okay, let's go to 1.782. So this is 1.782, but you see, remember, this is left-hand side, so put negative. If you're doing right-hand side, then it should be positive. But excuse me, I just realized I just made a mistake. The problem is 99% lower confidence bound. 95% is for upper confidence bound, so this is incorrect. Sorry about that. I should have done 99% lower confidence bound. So this is wrong. Let's go back to that t-table. All right, 99% confidence level. So 99% here, 1% there. I have to go to 1% column for degree of freedom of 12. 2.681. Do you see it? 2.681. It's in 12 column. 12 row, excuse me, and O1 column. 2.681. So 2.681. That's what I'm going to use. Again, why do I have negative? Because I'm looking for left-hand side endpoint. As a matter of fact, this is 99%. So I should have run 99% probably previously. Okay, and then let's work out this. It's not too bad. L minus of this quantity here is approximately equal to negative of 2.681, the t-score, times the standard error, which I'm copying and pasting. And then, of course, this center, I'm flipping over to the other side as well. That's it, isn't it? Flip it over. This minus 2.618 times SE, that was there before. So calculating this, punch into calculator, what do we have? 64.8811 is the 99% lower confidence bound. That is, there is 99% of chance the real mean is above that number. Real mean of these 13 women above that number. There's 1% of chance that real mean is by some strange luck 64.8811 or less. So why do we have this negative sign there? And in this Z table, or excuse me, in the T table, even though I looked up right-hand side tail and then got positive value, I artificially put this negative sign here. Why did I do that? Because I have to go to the left. For the right-hand side, I don't have to. It stays on right-hand side, so it stays in positive. So we get center plus the margin of error. Like the center plus the margin of error. But for left, center minus the margin of error. That's how you do confidence bound. Okay, so much for this example problem. And we have enough time? No, not really. So let me just open this up and then leave this problem to you. The density of the Earth is known to be about 5.517 grams per cubic centimeters. Henry Cavendish, an English chemist and physicist who lives from here, 1731 to 1810, was the first scientist to accurately measure the density of the Earth. Here's a data set based upon Higgs experiment conducted in 1798, and here are the real, actual historical numbers. You see, I like this problem because this problem clearly shows you that this T statistical analysis is highly realistic problem. We're doing highly realistic problem with, excuse me, not realistic, this is real problem. This actually took place in 1798. And then the answer key is here, but I'll leave the details to students. You'll have to find out the mean and standard deviation from here. It'll take some effort. Use technology aid and then calculate the standard error. Okay. And then before going over to this T-Taylor and T-computation, make sure you draw the picture. All right. Make sure you draw a picture. Like this. You want 95% upper confidence bound. So this is what we want. And then 5% to the right hand side. Okay. I'll stop here. The rest is left to the students. I strongly recommend complete this problem on your own. I may even assign it as homework problem. I have done it before. Maybe I'll do it again.